First example problem, we are given that sunlight of intensity 1 kilowatt per square meter is striking the black roof of a building. The roof of this building measures 15 meters by 45 meters. So the very first thing I'm going to do is I'm going to convert 1 kilowatt per square meter to watts per square meter, because we always want to be working in our base SI units. A watt is a joule per second. So a kilowatt would be 1,000 joules per second per square meter for when we turn into an intensity. So this intensity is really going to be 1,000 watts per square meter. Now we're also told that the sunlight is striking at normal incidence. Normal is a term from math. Colloquially, you could think of normal means perpendicular to. So normal just means the sunlight is striking directly onto the roof. So why does it matter that the roof is black? Well, a black object will absorb all light that hits it. And if we're talking in the context of photon pressure, it is important whether you absorb light versus reflect light. So the black roof will absorb all the light. All light that hits it. So in this case, the radiation pressure is going to be given by P is equal to I over C for perfect absorption. So in this case, the radiation pressure is going to be 1,000 kilowatts per square meter divided by the speed of light of 3 times 10 to the 8 meters per second. And I get the radiation pressure is going to be 3.33 times 10 to the minus 6. Okay, how are we going to use that to determine the force on the roof? Well, force is area times pressure. So if I were to say the force on the roof is area times pressure, so in this case I could say the force on the roof is 15 by 45 meters, length times width will be the area, so that will be 15 by 45 times the pressure. The pressure is the number that we just found of 3.33 times 10 to the minus 6. And then I put those numbers in a calculator and I find that the rate force of light hitting the roof is 0.00225 newtons. In the next example problem, we are told that a 75 kilowatt radio station is broadcasting uniformly in every direction. So let's draw a picture and think about what that means. We have a radio station where radio waves are being transmitted from a tower. So here's my radio tower. And the radio waves are being transmitted evenly in every direction. Now, if the radio waves are transmitted evenly in every direction, that implies that the radio waves, in other words, the light, is going to spread out in a sphere. So the power of this radio tower is 75 kilowatts. So the radio tower has power 75 kilowatt. And we always want to be working in base SI units, so 75 kilowatts would be a power of 75,000 watts. Now, uniformly in every direction, as I said, means that the waves coming from the tower are spreading out in the shape of larger and larger concentric spheres. So uniformly in every direction, in all directions, basically means spread out in a spherical pattern. So what is intensity? Intensity is basically the energy per area per time. So intensity is basically the energy, going to be the energy emitted per area per time. Now, power is energy over time. So here's an energy, here's a time. So energy over time is going to be the power, the 75,000 watts of this radio transmitter. What is the area? In this case, that the area of, just let's think about, I give a single signal out from my radio transmitter, and then that signal will spread out at the speed of light because it's traveling on an electromagnetic wave. And at some point in the future, that signal will be right here, comparatively. So this signal is going to be in the shape of a sphere that is moving away in every direction from the radio tower. At this moment in time, though, the signal is right here, a certain distance away. So the signal right now is a distance r away from where it was emitted. So the area of a sphere is 4 pi r squared. So the area, surface area of a sphere is given by 4 pi r squared. So the intensity is the power, energy over time, divided by area. What is the intensity of the radio signal when you're 250 meters away from the tower? Well, I could say the intensity of the radio signal is going to be 1 over the area, so 1 over 4 pi times 250 squared, times the power. Energy over time is power, so that would be times 75,000 watts. And I find at a distance of 250 meters away from the radio tower, the intensity of that signal is 0.0955 watts per square meter. So the way I think of that is, what is intensity? Intensity is like how much energy is striking a certain given area every second per square meter. So let's say this board is 1 square meter. That means every second about 0.1 joule of energy is going to strike this board. So now notice that the intensity of the light, or whatever type of signal is being emitted, is going to fall off as 1 over r squared. Because if the waves are spreading out in a spherical pattern, I could write the intensity of my signal, the intensity of the light, is given as the energy output divided by time, so that is the power of the signal divided by 4 pi r squared. And so the intensity is proportional to 1 over r squared. And so as you get further and further away from your source, the brightness of that source, how bright it appears to you, will dim as 1 over the square root of the 1 over the distance squared. And that's the same behavior we saw in a lot of physics. Whether it's also true for the gravitational force, g m1 m2 over r squared. It's also true for the Coulomb force between 2 charged particles, F is equal to K Q1 Q2 over R squared. And when we derived the Coulomb force from Gauss's law for electric fields, we found that this 1 over R squared term is actually a consequence of us living in a universe with 3 spatial dimensions.